What if the information you're processing right now, the thoughts swirling in your head, the words on your screen, what if that isn't just abstract? What if it's actually a physical thing? You know, as real as matter, as real as energy. It sounds a bit sci-fi, I know, but this is the core idea behind something called the Harmonized Informational Field, a concept put forward by Mr. Austin Maverix. Today, we're taking a deep dive into this really ambitious idea. It's aiming to be a unified theory, one that treats information itself as a fundamental physical field, underpinning everything from tiny quantum particles right up to the huge structures of the cosmos. So our mission here is to unpack this. Why even propose something like this? How does it try to link quantum physics, neuroscience, and cosmology? Seems like a stretch, and importantly, how could we possibly test something so grand? You brought some fascinating bits from the paper. Harmonized Informational Field, unifying quantum, neural, and cosmic dynamics. Let's try and make sense of it all. Okay, let's unpack this. So maybe start with the why. What's the motivation here? Why are researchers suddenly looking at information as this, fundamental force?
Well, it's a really interesting question, and the answer is that information has sort of organically emerged as crucial in fields you wouldn't necessarily expect to connect. Take quantum gravity, for instance. There's this major concept called the holographic principle.
Right, I've heard of that.
It basically implies this profound link between the geometry of space-time and the information it can hold. It suggests that the max information in any region scales with the area of its boundary. Think of it like a cosmic speed limit, or maybe a data density limit. The surface area limits the information content inside at about 1 bit per Planck area. What's really key here is it shows a universal relationship. Geometry and information, they're tied together.
Okay, so not just abstract math, but information is almost a physical property of space itself.
Exactly, that's the implication. It's not just in space, it is part of space in a way.
Wow, okay. But then how does something like that connect to, well, our brains? That seems like a huge leap.
It does, but look at neuroscience separately. It's pretty much established that the brain's core job is processing and integrating information. That's what it does. We can even model brain activity, neuron firing patterns, using things called neural field equations, like the Wilson-Cowan equations. These describe how large groups of neurons act over time, essentially as a continuous field of activity.
A field of information processing.
Precisely.
Yeah.
And then, if you zoom all the way out to cosmology, even the universe as a whole can be seen through an informational lens. Seth Lloyd calculated that the observable universe has performed something like 10 to the 120 operations.
That's a huge number.
It's astronomical, on about 10 to the 90 bits of information since the Big Bang. So the universe itself looks like a giant computer, in a sense, a massive information processing system.
Okay, I see the thread now. Quantum scales, brain scales, cosmic scales. Information keeps popping up as fundamental. So the next logical step, I guess, is asking, if it's that fundamental, can we actually define it as a physical field, like magnetism or gravity? Which brings us to Maverix's DIE, MathBFXT, this informational field. What is that, technically speaking?
That's the core proposal. And it's a big step, moving from information as a property to information as a field. So the framework defines I-MathBFXT as a local scalar density. You can sort of picture it as bits per cubic meter at any specific point in space and time. It quantifies the physical information right there.
Okay, like an information density map.
Exactly, and it connects to measures we already use. In quantum mechanics, it relates to von Neumann entropy, a measure of quantum uncertainty. In classical systems, or like in the brain models, it relates more to Shannon entropy, which measures unpredictability or classical information content. So Euler becomes this kind of universal translator for information across different domains, usually taken as a basic unitless density like $all. And the really big idea is that this field, R, isn't static. It has its own dynamics. It obeys its own field equation.
Like Maxwell's equations for electromagnetism.
Similar idea, yeah. Derived from an action principle, like other fundamental fields, it's described as behaving sort of like a wave, or maybe diffusion. And it has sources. Things like energy flows or neuronal firing in the brain would actually create or change this field. There's some key assumptions, of course, like additivity, locality, that you can smoothly average out the tiny details to get this continuous field. And that basic thermodynamics, like the second law, entropy increasing, still applies to this field too.
Wow. Okay, so information isn't just being processed, it's this. Stuff that flows, spreads, changes, according to its own physical laws.
Yeah.
Maybe even has a propagation speed.
Potentially, yes. That's implied by treating it as a field with wave-like properties.
That is genuinely fascinating. It really shifts the perspective.
Okay.
So if we accept this idea of an informational field, $1 for a moment, the ambition is to use it everywhere. How does it supposedly manifest differently at these vastly different scales? Quantum, neural, cosmic.
Right. The goal is integration, showing it's the same underlying field,
Yeah.
just behaving differently depending on the context. So at the quantum scale, Linder-Lawlers is related to things like entanglement and quantum coherence. The really interesting connection, again, is to space-time geometry. You mentioned the holographic principle. Related ideas like the Ryuta-Kayanagi conjecture explicitly link entanglement entropy, a measure of quantum connection, to the area of surfaces in space-time.
Entanglement actually building space-time.
In a sense, yeah, or at least being deeply related to its structure. In this HIF framework, it means a patch of space-time inherently carries an information density, IQ Mahler, related to its area. It generalizes black hole entropy. And the really radical suggestion is that gradients or changes in this $I field could actually source space-time curvature, could slightly modify Einstein's equations for gravity.
Information bending space-time.
That's the implication. Now, moving up to the neural scale, our brains, we already said they're information processors. The framework models the large-scale activity, like firing rates across brain regions, using those neural field equations as a direct manifestation of this dollar field. So our thoughts, our perceptions, they are, in this view, patterns and dynamics within the informational field of dollars.
Okay, that connects brain activity to the field. What about the physics of it?
Well, that raises the question of cost. If the brain is manipulating this Aldara field, processing information, does it cost energy? And the answer seems to be yes. Landauer's principle in physics states that erasing one bit of information must dissipate a minimum amount of energy as heat. About kilobarity TLN to 2.
Tiny, but fundamental.
Exactly. So this links the dynamics of the Euler field in our brains directly to thermodynamics. There's a physical cost to thinking, to forgetting. The paper also mentions integrated information theory, IIT. That's a theory trying to quantify consciousness with a measure called phenomenology integrated information. So in principle, you could calculate Lamb-Beat effects to $2 from brain scans and see how it relates to IIT's predictions about consciousness.
So every time I struggle to remember my password and finally give up, my brain is literally radiating a tiny puff of heat from erasing those failed attempts. Maybe that's why my head feels warm.
Huh. Well, maybe not noticeably warm, but fundamentally, yes, energy dissipation is happening according to this principle. And then finally, the cosmological scale, the universe again. It adheres to overall information limits, like the Bekenstein bound. There's speculation that quantum fluctuations way back during cosmic inflation might have encoded huge amounts of information, maybe 10 bits, into the pattern of the cosmic microwave background radiation.
The leftover heat from the Big Bang.
Right. And the theory goes further, speculating that this cosmic outer field could interact with things we don't fully understand, like dark matter or dark energy. For instance, if the Dahl field had a slight negative pressure, kind of like stretched elastic, it might contribute to the accelerated expansion of the universe.
Whoa, so information could be pushing the universe apart.
It's a speculative possibility within the framework, yes. It would mean adding an informational pressure term to the standard Friedmann equations describing cosmic expansion. That would be a massive deal, if true.
It's almost overwhelming. Information isn't just in the universe, it's potentially shaping it. Shaping space-time, setting energy costs for thought, maybe even driving cosmic expansion.
That's the core vision, yes. Elevating information from just processed data to a fundamental active ingredient of reality.
It is mind-boggling. But, okay, a vision is one thing. Science needs tests. How on earth do you test a theory that spans quantum physics, neuroscience, and cosmology? It seems almost untestable.
That's the crucial question, and the paper does address it. They emphasize that the framework has to be falsifiable, meaning there have to be ways to prove it wrong, and they propose several concrete tests.
Okay, like what?
Well, one is quite direct, building on Landauer's principle. Measure the actual heat dissipated by real neural circuits when they perform tasks involving information erasure. The prediction is very specific. A minimum heat cost of kiloby T ln2n2 per bit. It would require incredibly sensitive detectors, microcalorimeters on active brain tissue, maybe slices in a lab.
Okay, difficult, but potentially doable.
Right.
What else?
Then there's the connection to consciousness and IIT. If focused awareness corresponds to high integrated information, the prediction is that brain states during demanding cognitive tasks should show higher values of certain information theoretic measures. Things like neural complexity, which you could calculate from high-density EEG or fMRI data, comparing focus states to, say, just resting.
So comparing brain data during meditation versus solving a hard puzzle.
Sort of, yeah. Or focused attention versus mind wandering. The patterns of information flow, captured by Y$ should differ measurably. They also suggest looking at quantum neural networks, QNNs. These are like early-stage quantum computing systems modeled on neural networks. The idea is that if information processing has this fundamental nature, maybe QNNs based on, say, photonics, could outperform classical computers on certain tasks, like pattern recognition. You could run benchmark tests.
Comparing quantum versus classical AI, essentially.
Right, looking for specific advantages predicted by this informational framework. And then back to the cosmos. Upcoming experiments mapping the cosmic microwave background or large-scale galaxy structures. They are essentially mapping information distribution. The theory predicts these structures shouldn't violate the holographic bound. The total entropy, the information content within a large volume, say, our observable universe, should be below a certain limit, around $10 in Planck units. If we measured more information than that limit allows, well, that would be evidence for something new, perhaps new informational degrees of freedom or a flaw in the theory.
I noticed they also mentioned a fun test comparing brain networks to cosmic structures.
Yes, that one's more of an analogy, as I point out. There are some interesting visual and statistical similarities between neuronal networks and the cosmic web of galaxies. Both seem to be about 10% active nodes and 90% background. You could compare their mathematical properties, like power spectra, but finding similarities wouldn't prove the HIF theory. It's more suggestive, maybe. An intriguing parallel.
Important to distinguish analogies from hard tests.
Definitely. And they also do something else that's scientifically important. They propose tests that are likely to fail based on current understanding.
Why do that?
It shows rigor. For example, they discuss testing for quantum coherence in neural processes using something called Leggett-Garg inequalities. If brain processes were fundamentally quantum coherent over time, you'd see certain violations. But based on physics, the warm, wet brain environment should cause extremely rapid decoherence, meaning quantum effects shouldn't last long enough to be detected this way.
So they predict this test will likely show no quantum effects.
Exactly. Predicting a null result and explaining why is also part of good science. It shows they aren't just cherry-picking potential confirmations. It makes the framework more robust by defining its limits.
That's actually quite reassuring. It shows they're thinking critically about their own proposal. Okay, this has been a massive deep dive. We've gone from quantum entanglement, possibly shaping space-time, to the heat cost of forgetting a password, to information maybe pushing the universe apart. Taking a step back, what's the big picture here? What are the main strengths and where should we remain, skeptical?
Well, the harmonized informational field is definitely bold. Its big strength is providing this potential common language information to talk about physics, neuroscience, cosmology all at once. It suggests new mathematical tools like these informational field equations. And crucially, as we just discussed, it makes some predictions that are, at least in principle, testable and falsifiable. That's key.
But the speculative parts.
Oh, absolutely. We have to be really clear about those. The very idea of information being a fundamental physical field is not standard physics right now. It's a major conceptual leap. Assuming you can just smoothly average out discrete bits or quantum states into this continuous field I$ that glosses over some really complex physics, it's a strong assumption. And the proposed couplings, how I$ might influence gravity, or how neuronal firing acts as a source for A$, these are currently conjectural. They need theoretical development and experimental evidence.
Right.
The authors are commendably transparent about this, though. They even explicitly call the idea of, say, changes in cosmic dark energy directly influencing conscious experience via the dollar field a wild hypothesis with no current evidence.
So acknowledging the speculation is built in.
Yes. But despite the speculation, there are these empirical hints that point in a similar direction. The idea that quantum entanglement is related to space-time geometry is gaining traction in theoretical physics. The success of those coarse-grained neural field models does show that you can capture high-level brain information dynamics with field variables. And the whole notion of the universe as a quantum computer processing information, it makes thinking about its dynamics in informational terms seem less, well, crazy. It might just be a very useful perspective.
So it's less a finished theory and more A research program, a new way to look at things.
That's a good way to put it. It's a framework of vision, trying to harmonize very different scientific domains under this umbrella of information. Rigorous where it can be, but open about the big leaps it's taking. It's really an invitation to explore reality through this informational lens.
We've certainly taken a deep dive today into the harmonized informational field. It's a theory that really dares to connect the dots, from quantum mechanics to our own consciousness, all the way out to the cosmos, using this single concept, information.
It is a powerful reminder, I think, that the universe might be far more interconnected than we typically assume, and that maybe the biggest breakthroughs come from looking for principles that span across disciplines that seem totally separate.
So the final thought to leave you, our listener, with is this. If information isn't just data we process, but an actual physical field woven into the fabric of reality, how does that change things? How might that shift our understanding of consciousness, of space-time, maybe even of life itself? What does it mean for us and our place in this potentially information-based universe? That's something to ponder long after this deep dive.